There. Finally. Questions on what we just covered? Why? Anybody want to ask why? Why is a great question. How many of you would actually do this in days? Nobody. Fair.
I'll ask a question.
Yeah.
How do I know this model is any good?
Great question. We don't yet. We just ran models. It was like model soup. Throw every model in, and we have no idea. We are going to talk about that next. So the plan for right now is that we are going to talk about, here we got some auxiliary things. I'll just leave that for now. Bayesian psychometric model fit methods is really what we're going to get into. This will likely cover up to lunchtime. Then you will not hear from me again for a while. Actually, that's not true. Lisa and I will change roles, and it's Lisa time this afternoon after lunch, after the keynote.
But you'll do the Stan parts.
But I will be interjecting with Stan. Yes. No, let's just talk about why. Why would I pick an IRT, Bayesian, for a very simple IRT model? There would be two reasons I would pick it. I do a lot of work with school districts in the United States, and a big focus of the work we do is on small, short, formative assessments, 5-item quizzes that students might take in the middle of instruction. And I don't have a lot of data, and I don't have a lot of items, and I find I can do things in Bayes that have things converge where I can't easily in other systems. So I find Bayes to be flexible for that. The other reason is multidimensional IRT models. The estimation of multidimensional IRT models is quite difficult from marginal maximum likelihood. We have shortcuts that we've done, either least limited information, like a weighted least squares, diagonally weighted least squares, or we have an EM algorithm that actually uses Bayes in the middle, the Robbins-Monroe algorithm, but it's pure EM algorithm will take forever because of the integral that passed through it. So I don't usually use Bayesian methods in IRT, just unidimensional IRT for what I do. I'll also add the little 5-item tests I do. I like to estimate a 3-parameter model. So having a prior on the C parameter makes me happy, but then again, that's nothing new. The C parameter has been causing problems since it came about, and even in the 1980s, the Bilog program used a prior on the C parameter by default. So, but it would just estimate it in an optimal sense, not a sampling sense. So, but we do use Bayesian methods for IRT. I will now add how do we use model fit for it. We will do 2 types of model fit. Absolute model fit, whether we fit the data absolutely. And then we will do relative model fit. And actually, I'm not going to use the methods for relative model fit. I'm going to use something called LOO, leave one out. I do not want to call it the English word because I don't like saying that word. But otherwise, LOO, WAIC is another recently one. I think if you started back in about 20 years ago in literature, you'd see BIC, Bayesian Information Criterion, a lot in Bayesian model fit, but it's since been replaced by these 2 statistics in more recent years, and so we're going to build those as well. But let's start with absolute model fit. The first thing we need to know is does our model fit the data, to the data sense, not relative to other models, but the data sense. So, psychometric models, we do need to check whether the model fits the data absolutely. If you're familiar with this in a structural or a confirmatory factor analysis perspective, absolute model fit sometimes is in the form of the comparison of your model to what would be called a saturated model, where we estimate all the means and covariances and variances unconstrained. Oftentimes then we summarize that either using a model chi-square, which usually is significant, so we conveniently ignore it, or we talk about the approximation to model fit with the statistics like root mean squared error of approximation. Alternatively, there's another statistic called standardized root mean squared residual, which is a comparison or sort of the standardized version of how far off you are from each of the covariances in the model itself. the methods that we will use is much more like that ladder statistic. So, in posterior predictive model checking, how many of you have heard of this before? A few. Bayesian statistics, the way that we check whether our model fits the data is sort of an odd, very similar to the Markov chain itself, is to simulate data sets using the parameters drawn from each iteration or from sampled iterations, and to see if those simulated data sets in any way resemble our real data, right? So, in each iteration, we don't have to do each iteration, we could take a sample, but you can code this in Stan to do the work for you, for most of the work for you. We are going to, at each iteration of the chain, take all of the parameters of the model and simulate data as if those parameters were the true values. And so the data we're simulating is the same shape, same size, same number of items, same number of people as we have in our data set. But every time we draw a new set of parameters, we resimulate data. And then now, if you think about it, from this last analysis, we saved 500 iterations at the end of each chain. There were 4 chains, so that's 2,000 saved values. We will have 2,000 simulated data sets. That's a lot. So how do we compare and contrast? What we will use are summary statistics of our data sets, right? We will compute, so let's think of it this way. For each simulated data set, we can easily save, say, like an item mean. We're not going to use an item mean, there's some problems with it. We will usually fit an item mean almost perfectly. It's saturated. But for purposes of illustration, let's envision this, right? Let's take the first item. We have 2,000 simulated data sets where we have 3,100 responses to the first item that have been simulated. What we could do is turn those 3,100 responses into a proportion of correct. Right, so now we have 2,000 samples of a proportion correct for the first item. So what we build from that is what we call a predictive distribution. So we build a nice distribution from that. And for that distribution, we then compare where the observed proportion correct was with the distribution of our simulated proportion correct from our sampled values. And sure enough, if the value of the observed proportion correct is in the center of the distribution, we think that we are doing a fairly good job with our model recovering that statistic, that feature of the data. But if for whatever reason our observed proportion correct is in one of the tails, or maybe the highest value, or maybe the lowest value, that indicates our model is not recovering some feature of our data well. And that's the misfit that we're starting to get. We start to quantify. So that is the way that posterior predictive model checks work. You will see all sorts, there's not a good standard for use of these. In fact, most of the times I see people use this, I think it's to confuse, in research literature, I think it's to confuse reviewers who aren't experts in things. Because they'll do things like the proportion correct for each item. Well, it turns out each item has its own parameters, at least for the 2-parameter model. The parameters are the same for every item. And there's an item intercept in the 1-parameter model. So you can imagine, unless we put prior distributions on that are really really highly informative, we're probably going to get a proportion correct or a distribution of proportion correct somewhere in the vicinity of that for each item. So the univariate statistics that you see, item mean, you can come up with a chi-square, I tend to think they're useless, but you see them in literature from time to time. So what we're going to do is sort of mirror what happens in confirmatory factor analysis. We're going to look at building statistics of bivariate measures. For binary data, I like to use something called the tetrachoric correlation. How many of you are familiar with tetrachoric? No. Let's describe tetrachoric correlation for a moment here. I did get the iPad ready. Let's see if I can.
Yeah, you gotta draw so the recording can.
That's right. Okay, so first things first. If we have 2 variables, x and y, and we have a contingent, they're both binary, 0, 1, 0, 1, we can build a contingency table for these, right? And there will be a probability for each one of these. Probability 0, 0, probability 0, 1, probability 1, 0, probability 1, 1. We could easily take a Pearson correlation or a Pearson covariance, but there's a problem with that. In binary data, the Pearson correlation is truncated unless you have identical margins for each observed variable, so each proportion is about 0.5, right? And so we shrink the boundaries. Normally we're used to correlations going between -1 and 1. The Pearson correlation actually has a range less than that, depending on which marginal proportion of people are in each value for x and y. So instead, the tetracork correlation tricks us into thinking, what if we really didn't have binary data? What if it were the result of assuming that we had some continuous x, maybe I'll call it x star, and some continuous y, y star. Okay? So now, we don't have a continuous x, and we don't have a continuous y, but let's pretend that we did for a second, right? Moreover, let's pretend each one of them were normally distributed by themselves, univariate normal, right? So x has a univariate normal distribution, y has a univariate normal distribution, right? If we did that, we wouldn't, just like in other data like our psychometric models, we wouldn't have a converged, we couldn't estimate a mean of x because it doesn't exist. We couldn't estimate a standard deviation of x star, because it doesn't exist. But what we could do is we could fix the mean at 0, fix the standard deviation at 1. So now x star has the standard normal distribution, right? So if I just looked at x star by itself, whoa, that would have been fun. Almost fell down. Here's x star. Here's the standard normal distribution, mean 0, variance of 1. If we wanted to figure out the marginal proportion of x star, xp1 dot, we would find a shaded area above some threshold for x. And this area under this curve would equal p1 star. And that's the probability of a 1 for x. We could figure out the threshold that corresponds to that value, because we fix the mean, we fix the variance, we have a standard normal curve, we figure out from the p norm function or the q norm function in R what the proportion is below the curve, and then 1 minus that is p1 for the x above it. So that's what we believe about x star and y star. We have some type of cut point for each one, tau x, tau y. And that segments this chart into 4 regions, right? Above x and above y, this is p11. Below x, below y, this is p00. And then we have each of the other probabilities listed. Okay, so what happens in the tetracork correlation is when we put the 2 univariate distributions together and assume that they're bivariate normal, or multivariate normal with 2 dimensions, right? The multivariate normal with 2 dimensions, we'd say x star, y star, distributed normal. The means are 0, mean vector is 0. The covariance matrix has 1 for the diagonal, but we could estimate the correlation between the 2, that row. That correlation is the tetracork correlation. And the way that we do that, if you've seen a multivariate or bivariate normal distribution, I'm going to look at it from the top, like a contour plot. So like the shape of it, as you go up, the higher up the contours are lower. I'll draw regions of equal height here. We could draw basically a bivariate normal distribution here, like that. So we're looking at the top of it. These are contour lines, like a hiking map of where you're going if you're hiking. So now we need to figure out marginally, we can figure out for each x and y the threshold pretty easily. That's still, the z-score to which divides distribution. But we optimize, or we figure out from this bivariate normal, the correlation, rho, such that the probability for each of these quadrants matches the probabilities in the table above, right up here. It's a little weird, but it's doable. And that gives us a correlation that ranges from -1 to 1. So, how are we doing? I've just gone down yet another path of craziness. So why do I do it this way? I like tetrachoric because I think it's a more accurate version of model fit. I think because of the boundary issues with Pearson correlation, or the covariance, the numerator of that, where we unstandardize the correlation, I think it's, when you look at real data analyses in Bayesian statistics, it's a lot easier to fit the covariance matrix than the tetrachorics. Question?
I just know you could use it to, for example, to estimate CFAs.
Yes.
If you use these limited information.
This is the input to limited information. That's correct. That's it. If you look at using item factor analysis, the default in M+, and what Levon uses, this is the summary statistic of the data that it uses to do factor analysis on. So item factor analysis uses the tetrachoric correlation in its estimation.
But only if you define ordered items and a lot more.
That's right. Levon used to say the items are ordered, and then it switches. It is using, instead of the multivariate normal likelihood with the data, it uses this likelihood function here. And instead of the correlation there, it uses what the expected correlation would be under the model parameters and stuff. But with that, though, that's where, if you're used to limited information, if you may have heard delta versus theta method, the reason why we have to pick a delta or a theta is we have to keep this diagonal 1. And there's two different ways of doing that.
That's delta.
What's that?
That's delta, if the total is 1.
Well, yes, otherwise but either way, we still have to keep it that way because it doesn't exist. So, okay, other questions? This is tetrachoric. It's, I remember Rod McDonald said, we just use tetrachorics. He had a program called No Harm. Oh, yeah. You just use tetrachorics, call it good. I was like, I have no idea what you're talking about. Right? Yeah, then as a full professor, or almost full professor, I was like, how does that work? So I did a little snooping. The tetrachoric, the likelihood for a tetrachoric is that multivariate normal. And actually at the top of my syntax, you'll see a function that says build tetrachoric PPMC. I cannot get Stan to estimate a tetrachoric because the tetrachoric is actually a function, it's an optimal value for that likelihood function. So instead, I go and I build a function called find tetrachoric. This requires a package I wrote, talk about pun, blatant, Bayesian latent variable model. Sorry, never mind. The English word blatant is usually spelled with an A, but there's an E because it's a latent get. So, never mind. Anyway, this is diagnostic models in Bayesian. That's where it started. And then I quit developing it because I got tired of it and I don't have any time for it. But the point of the matter is, if you look at that function, it will calculate a tetrachoric correlation matrix for you using what I had just shown before. It uses the bivariate normal likelihood function to build it, and it estimates it. But what we are going to do with this is we are going to submit, we're going to take all of our simulated data matrices, give it to this function, and it will calculate the tetrachoric correlation between each pair of items. So now with 10 items, we have 10 choose 2 correlations, which is, I believe, 45 correlations. So we're going to go do that real quick. So,
Real quick.
real quick. Let me do that here. I'll get to the problems after I show you what I'm doing. Yes, real quick, Lisa, real quick. First, I want to show you the Stan code for it, though. In Stan, there's another block called generated quantities. Generated quantities is actually, as described, it generates numbers based on the values that just got sampled in the model block. So this does not affect your model. This is basically anything you want to compute later on that you can build yourself. Where would you use generated quantities? You mentioned estimating like a McDonald's omega. You could use this to calculate McDonald's omega from every iteration of the chain and build a posterior distribution with it. For generated quantities, we also can simulate data in it, and that's what we're going to use this for. So in generated quantities, we again have to define a data set. Actually, I use generated quantities here to express item difficulty rather than item intercepts. So you can actually look at that as well. I didn't mention that because time issues, but that's what I did. SimY is our simulated data set. We define it as if it were a variable, like in a parameter. So we have to tell it it's an array, it's the same size as our data, and it's an integer. And then this is where it does slow things down. I cannot just do the vectorized form here. I have to loop over items and people. But in SimY, there's a function in Stan. Every distribution and function has this ending to it, RNG. It stands for random number generator. So Bernoulli logit RNG will generate a Bernoulli variable using a logit length function for the term inside the parentheses. So for every item and every person, I'm filling in this SimY data set, which is 10 items by 3,100 observations, with the current chain values of the parameters that are highlighted right there. So it is building simulated data sets from where I go. And you'll look, our model is Bernoulli logit with those values. Our simulated data is Bernoulli logit RNG with these values. So it's not that different. It's just an added term to build that. The model output now, though, is extensive. So that means we now have, for every sampled value of the chain, right, after warm-up, a data set that's 10 by 3,100. That's a lot of information. So that is why I created that function, build tetrachoric PPMC, that will submit the samples. So basically I grab our samples from our draws, where the variables are SimY, in a format of a draws matrix, and then I loop through every sampled covariance, or every sampled data set, and build a tetrachoric correlation matrix for every one. That's how it works. So here, I can quickly show this. I don't know why I'm overwriting the raw data, but I do. I grab 2PL samples. Do that real quick. Everything is in quotes. It's not real quick. No, what did I do wrong here?
I quit saying that now.
Yeah, I do.
There's no such thing as real quick in Stan.
True. I have it right here. I'll do the 1PL. So there, and now I run this, and it does take a while, as you imagine, but at least I put a little status bar on there. Go, 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 go. So, anybody got any good jokes? I feel like if I built Stan, it would just play music while this was happening, right? Actually, that would drive me crazy. Shut up.
Maybe I can ask a boring.
Yes, please.
How much RAM does or memory do these samples take? Like you actually have iteration number times 10 times 3,000.
A lot.
Yeah.
But I have 16 gigs on this little computer here. And the file object itself that saved it, the compressed version of it, for this was somewhere between 70 megabytes and 136 megabytes. So depending on, it does take quite a bit of memory.
Then Sten does Sten just write this output after each iteration to the local computer and then empties it?
I'm not sure. The writing process slows the simulation down. So yeah, it makes it about 3 or 4, depending on the speed of your disk and whatnot, takes quite a bit of time. But I think at some point it does, and I think it actually writes it to disk after it's done, because I have exceeded memory. Actually, on a high performance computer, I didn't ask for enough memory for a slot, and it stopped. So, but it is a very good question, big concern for it. But now I'm finished with PPMC, and now I can take a look. The PPMC statistics here, I have, actually let's do this. Nope. Well, that's a list. Huh. There we go. Okay. So what I've done is, what that does is it compiles for each pair of items the observed tetrachoric correlation. So the observed tetrachoric correlation between item 8 and item 9 was 0.7786. So then the rest of my PPMC statistics is the distribution of tetrachoric correlations that I just sampled. Right? So I don't visualize it here. I probably should have done that for didactic purposes. But you can envision there's a posterior density of tetrachoric correlations now from these items. We don't call it posterior, we call it a predictive distribution instead of a posterior distribution, because we're essentially predicting it by simulating the data. The mean of that predictive distribution, the tetrachoric correlation mean is 0.4512. So we observe 0.7786. We believe the predictive distribution thinks it should be 0.4512. So over here is the raw residual of 0.3273. We can see the standard deviation. I also provide the 90% credible interval. So what we do, though, what you can see is this column is the 5th quantile. This column is the 95th quantile. So we're between 0.40 and 0.49, or 0.4 and 0.5. Right? So our predictive distribution is centered around 0.45. Our observed value is 0.77. So what we need to do to tell, an easy way to check, is that in the tail. If you think about it, that observed value is way in the tail of the distribution. It's certainly above the 95th quantile, right? So if we go and calculate, what I do is I calculate what's called the posterior predictive p-value. I know that makes the Bayesians all shudder. Oh my goodness, it's a p-value. Can't do that, it's Bayes. Bayesians don't have p-values. Yes, we do. Until we do, and we need one. That's another topic, by the way. Each of these is a maximum likelihood estimate, point estimate.
I was going to ask
But, sorry. We're Bayesian until we can't be. Anyway, that posterior predicted p value basically is the percentile rank of where the observed tetrachoric correlation is compared to the predicted distribution. And it's at 1, meaning it is the highest value. So this model is underestimating the correlation between items 8 and 9 quite severely. All right. So this says, hey, in terms of local misfit, this would be like this residual right here is like a raw residual of a correlation matrix in factor analysis. It's the closest thing we can get. But we can tell there's misfit here. I put a little marker there. If the p-value is above, I think, 0.95 or below 0.05, I've highlighted, these are the items, this TTC flag, tetrachoric correlation flag, flags the items where the tetrachoric correlation p-value is in the tail. And this is the set of items where that happens to be. So, what do we do with that? Now we have 45 pairs of items and a whole bunch of tetrachoric correlations. And that's where the Bayesian model fit stops. Well, not really. There are, of course not, right? The facial expressions are great. I like it. You know, it's good. I like it. I like it. It just reminds me, yeah, there's more, but there's more. No. This is not a overall model fit test statistic. Actually, just a former PhD student who's starting an assistant professorship at the University of Arkansas, his dissertation was on model comparison with what we would call limited information model. So we fit a model that would be saturated to the two-way tables that we have here using a Bayesian network, and then we did a model comparison between that. And that statistic using model comparisons is effective overall, like a M2 statistic, but we haven't implemented it easily yet in R for other people to do it. Only us that really love being in code do that right now. But that's where it's going. So this is the local misfit. I can't tell you global from this, but that's what I've got. Questions? Lisa looks, what's that look on your face?
It's not a question, I just had 2 comments.
Mhm.
So, number 1, the observed is a single number, but isn't that really like a distribution too?
And that's why we worked on the research that led to his dissertation.
And
Yes.
the other thing is that almost all of the estimated model estimated correlations are about 0.45, because this is the one parameter model
Yes.
that says all items are equally good and equally related. So this is a consequence of the model, not a coincidence.
This is exactly right. That's right. So the one parameter model, this is what you get. Would you like to see this for the 2 parameter model? Let's do that.
Should be better.
It should. I actually also built a heat map of this. I don't know if this is very helpful though. This is where the biggest is. But the heat map's all relative to where it goes in terms of it. But
Is the black the bad? in that?
I think so. Now, these are the heat map of the residual values. So the black should be the more extreme, but I'm not sure. Let's do that for the 2 parameter. Here we go. Okay. Yes.
Can I ask a question?
Yes, please.
I somehow got lost a little in the bigger picture.
Okay.
So what we're doing now is model fit and looking at the correlations of the items and whether the observed correlation fit what the model would predict.
That's right.
And because we assume in the model that the correlation is like equal, we get equal estimates and see in the observed values, okay, maybe this is just sometimes not true.
That's right. Yeah.
And when we see this, like actually we saw it now, that something is wrong, this is telling us that model fit isn't
Correct.
good.
That's right. Yeah. The more that we have flagged in the tail of that distribution, that means the more correlations our model doesn't fit well. That means cumulatively the model is not working well. Now I don't know where we would say it's bad model fit from good model fit. That's the problem with this approach. But yes, that's what we would say.
And then we would, in a second step, maybe adapt the model and
Yes.
see, okay, maybe there is something that the items share that is not the latent variable we assess, so maybe we need another one that is capturing that.
Correct. That's right. What I like to do with this information is I take a look at the items where the the observed tetrachoric correlation is too high or too low, and I sort of tabulate which item shows up the most in those misfitting, and I try to look at that item and say, what's going on with this item compared to the others? And I keep that process going. Or another way is, like you say, you look at pairs of items and say, what's in common with this 2 that isn't in common with others as well? And that gives us a sense for how to remedy the misfit.
And this is a way to check that it's important that the residual variances, they don't correlate. Or if they do, we can apply in the model.
Well, in this case, yeah, the binary item model, there actually isn't a residual covariance. And to fix this, because we're in full information, it's actually quite complicated. It's either add another latent variable that only measures a pair of items, but with some constraints to ensure that it's identifiable, or to change the distribution from a univariate Bernoulli to something that's multivariate, which is a little bit harder. It's usually a log linear model of some sort that provides that. So it becomes a little bit more difficult. So, sorry. Feel like I should apologize. Yep, this is complicated, but yeah.
Thank you.
Thank you for your question. Lisa, is this what you were expecting?
Yeah, they're all still sort of compressed to the middle
They are.
for the most part.
They are.
Are there any heuristics as to how many, like, you would expect to be out of bounds?
I'm not aware of them. I wish that, there you go, that we need more study of this. I think oftentimes either people are using this in their applied research, empirical research, to study a phenomenon, and then, they just report this is what we have. Or, we have people who've studied a little bit of this before, but I don't know there's a conclusive study I can point to that I know of that says this. There may be a conclusive study out there that I'm just not aware of.
Dissertation opportunities, anyone? Figure this out for us, please.
So again, the problem with this, there's no uniform standard of which statistics to use. I'm using tetrachoric correlations. In fact, I'm one of the few that do that. I'll admit that. But why I do that is because in my practice applying this to data, I can tell you that the fit to the tetrachoric is much more difficult to achieve than fit to Pearson. Like if I were to try this with the Pearson correlation, I may only have a couple correlations that I misfit. Like it's usually much lower. Yes?
So suppose that you have Likert scale data, should you then use
Poly.
the Pearson or the polychrome?
Well, that's a good question. I don't know. At some point, maybe 5 or more options. You switch over. I don't know the answer to that. But the polycork would fit well into this framework pretty quickly. And you could use this to calculate, I wouldn't say quickly, but you could build a similar function for polycork that would do the work this does as well too. The psych package in R has a good polycork function that actually the one from Blayton ripped psych off or borrowed since it's open source, based it on that, but there's auxiliary information in psych that I didn't want to have because I'm using this multiple times. So I cut out the auxiliary stuff and just used it. So you could do that, take the function I built and switch out the Blayton function for polychoric and have that be achieved. Also, I mentioned, there's no global indices of model fit here, which is really dissatisfying. Like, I really wish I could see that, like a one number summary. Would be nice. I mentioned my former student, Jihong, has a paper on this in structural equation modeling. We try to mirror the M2 statistics with PPMC. And I think there could be, actually this is working on publishing, that's not true, it is published. Actually, no. A different paper is published in structural equation modeling. His dissertation is under review right now, so we're getting that, working on getting that built. The other thing that is interesting about this is that there's no penalty for too many parameters. The remedy for this, as we mentioned, is to make your model more complex or remove items. That's more often the case than not. Oh, these items didn't fit. Well, I don't need those items. Just forget about validity. Just remove those items. So it's possible that you can fix your model fit, make it look really good, but have so many parameters in your model that you don't need all of them. Right? You make a multidimensional model that just doesn't make a lot of sense. So fit will only improve to a limit with posterior predictive model checks. And that is one of the issues that we have. So, any questions about posterior predictive model checks? No. Okay. I mentioned that already. Do that. Let's talk about relative model fit then. This is where we get a penalty for extra complexity. I'll do this in a very non-technical fashion. We will use something called leave one out model fit. There's another function called WAIC, widely available information criteria, or Watanabe is the name of the person who came up with this. Both of these are relatively recent additions to the Bayesian literature. They're like 4 or 5 years ago, maybe 5 or 6 years ago with leave one out. Watanabe's statistic was 10 or 12 years ago, if I'm not mistaken. There is a bit of debate with this, though, because we estimate in Bayesian, the way that I've coded parameterized our model, we have estimated theta as a parameter. Whereas in frequentist land, in maximum likelihood land, we don't estimate theta, we marginalize across it. And so our model fit statistics are largely built on the marginal statistics, not with theta being estimated. So here, we could do this. We could build a marginal estimation of theta in Stan by literally building an integral into the algorithm itself. But that would slow it down even more, and I don't know that it's very useful. But the question I have, the thing I struggle with, and I don't see people talking about this much, at least I'm not aware of, is the comparison of model fit. If we fit a joint maximum likelihood model and we included theta in our model fit, would that change our model fit decisions in relative model fit? I don't know the answer to that, but that's what we have to struggle with here. So we're going to build theta into our model fit for relative model fit using leave one out, as we do. Here's how it works. What we need to build is something called the expected log posterior density for each person in Stan. The expected log posterior density. Let's think about that. What is the posterior density? And then what is the expected log posterior density? Well, I calculate this by building a person likelihood. So each person gets a likelihood value. And for each person, I calculate the likelihood as a sum of log likelihoods across each of the items. So I initialize the person likelihood to 0, and then I sum across each of the items the person log likelihood. And there is a function in Stan called log posterior mass function, PMF. It's a discrete distribution, probability mass function, excuse me. And what that function does is it tells you the likelihood of observing a person's item response score conditional on their model parameters themselves. So this is literally taking the Bernoulli likelihood for that person's observation at the current value of the parameters in the chain for that step. So what we end up doing is we're filling in data where we have 3,100 individuals. We're basically looking at the likelihood, or the log likelihood, of each of those observations at each iteration of the chain, based on the theta, the lambda, and mu, the item parameters, as we go forward. The Stan function for that is this Bernoulli logit LPMF. Each distribution in Stan has a similar function that you can build in as well. And so what we end up with this is we have basically a sum of log likelihoods for all of the items. It's like a person likelihood. This is the core of person fit statistics in psychometrics, actually. So we're talking about basically how likely the model thinks that observation would be based on the model parameters. And what we do is by summing across oddly items is seeing how likely the whole vector of items responses would be at each step of the chain for each person. The thought being this is the input then into the function that calculates leave one out. And that function, wow. I'm going to do this, the hand wave, because there's a lot of detail to it that I'm going to...
One what? Item or person or vector or what?
One what?
Leave one what out?
It's trying to simulate here what happens if we leave one person out. But it's weird because you're right. Leave one out could be one item per person. And I think the moniker leave one out is not necessarily the name of it, leave one out, is not necessarily a good one, but it's what it's trying to approximate if you have a cross-validation approach to model fit, where you look at, if I were to remove one person's data and predict it with the rest of the model observations, that is what leave one out is trying to approximate. Now, I would be happy to refer you to the paper where they describe this. I haven't fully ingested the details, which is dangerous, I know. But it is what happens. We then calculate for this something called the leave one out. Now it turns out there is a package called LOO in R that I loaded when I loaded stan, the CMD R stan. And if you have a variable where you've calculated that likelihood in generated quantities, it will do the work for you. Here is the fun part about that, though. What it uses is something called a PSIS. What is it? Pareto sampling importance, Pareto distribution importance sampling, to try to mirror what would happen if you had to leave one out. And it tries to tell you if things are really bad, and this is really bad, right? So this means don't believe the leave one out very much. And what happens in that case? I don't know that there's very good. But what this is doing is trying to come up with a version of a statistic like an information criterion. This is the leave one out information criterion right here. And it even has a posterior, like it calls a standard error, but it's like a posterior standard deviation. So we effectively built another distribution of that statistic itself in Bayes. This is not a reliable estimate of it, though. So that's what it tells you whether or not you can believe it. But here, you can then use a function instead called LOO compare, or the LOO package, LOO compare, and you can give it a list of models, and it will try, oops, I don't have it up here. Let me grab it real quick. It will compare the models themselves. Now we have to, I just showed you that the fit was bad, so it's not really trustable. But what it does is it tells you which model tends to be preferred. And in this case, it thinks the one parameter model is preferred.
What?
Yeah, that's weird. Actually, I think I'm reading this backwards. Hang on one second. I'm sorry, this is getting me past my limits at the moment. Here, let's put all three here. Yeah, so here, actually no, I'm reading this backwards. No, the one parameter model, the lower value is the preferred value, right here. And this is the standard error of the difference, right? So here, I apologize for my mistake there. Here I'm comparing the one parameter model, the two parameter model, and the two parameter with the marker item. And you'll see the numbers for the two parameter with the marker item are approximately the same, and that's because these two are the models that we work. This is, let's see here. And then we have our standard error of the difference as well. So the other thing that this builds in is a standard error statistic as well. So one of the things that you do in terms of model comparison, you may be familiar with looking at models from information criteria, like AIC or BIC, sample size suggested version. I mean, there's 15 of those, right? And you have these, and you look for the smallest value of it. This is not in the deviance formation. This is in calculation. This is in the, this is divided by -2, basically. This is on the likelihood side. But what this is telling you is basically there's a standard error around this value of these statistics. So it even gives you how much uncertainty it is. But, as we just saw, each of our leave one out calculations are not very good. So it's not really approximating the leave one out well. So yet again, a little dissatisfying for model comparisons. Yes?
So I get the numbers from model 2PL and 2PL marker.
Mm-hmm.
And then I like the smaller one is for the better model. But here we have negative values, so
That's right. It's on the different scale. That's right.
but then still the smaller one.
That's right.
And what about the zeros for the one?
That is where it basically is saying the least preferred, I believe, is at 0. If I'm reading this correctly, I'm making sure if I do this right. Okay, so the 1PL, leave one out, is actually a better fit. I think I'm reading this. Let's see here. Yeah, that's the problem. Okay, the problem we have here is the leave one out statistic for the 2 parameter and the 2 parameter. It's just not calculated well. So yes, I was correct in how I was reading it. It's preferring. I'm going back to my original interpretation. We would prefer the 1PL here, but that's not because the 1PL fits better. That's because our estimate of the statistic is better. For whatever reason, the statistic, the way that the LOO is calculated, is an approximation to the process of leaving one observation out and rerunning the analysis. And that approximation in each of the other models is poor. And so because of that, you look at the size of this metric. If I look at 1PL LOO, just the output from it. This case, only 9% are very bad. Most of it's bad. Still not a great approximation. They would tell you in the help for this, they tell you want most of it to be good or okay. That is not this case. We only have 30% of our data that are good or okay. This is the information criteria that goes with it. 30,118.4. That is on the deviance scale. So that's -2 times what is like a log likelihood. So the smallest value of that across all 3 models is the winner for this. And this is how much error is in that statistic. But the problem is, and this is what you can see pretty quickly, in this example, the 2 parameter model has very poor, very bad approximation. The 1 parameter had 30,000 here, and this has 168 million. So yet again, not a good approximation, not a good statistic. But this is supposed to be more advanced. Lisa is frowning too.
I think my head just exploded.
Yeah, I think mine is too. How many of your heads exploded? Anybody want to help me? But no, what's happening is, so going back to this, so what it's trying to do is, the people who came up with this statistic tried to mirror the process of leaving one out, leaving one observation out, as if we were, you can imagine how long that would take if we did this in frequentist land, right? We have 3,100 observations, leave one out, estimate the model, predict what that one should be. That process uses a sampling, version of sampling to try to sort of approximate what that process is, but it tries to tell you if that, it has some type of diagnostic information to say whether that sampling is acceptable. And in this case, it's not. So what we get from here is not good. Not good at all. And then there's let's see, there's a WAIC function also, widely applicable, widely available, information criterion. And here, I could also calculate it as well. But I don't think, I'm doing things that it probably shouldn't on the fly here. Yeah, well, let's see. Yeah, I don't have that ability to do that now. So, yeah, I think I'm going to stop there. So, not a good approximation. Yes.
So I can calculate the LOO for each model, and then I take the smallest value of that. But before I use that, I have to test whether the estimation of the LOO is good
Yes.
enough that I can use this value.
That's correct.
And if I could use all LOOs, then maybe I would go for the 2L model. But since I saw that for the 2 whatever models, I can't use it, so I go with the first model, which has a worse LOO, but the only one I can use.
That's right. And that's crazy because we just saw from an absolute sense the first model fits worse.
Yeah.
Right? Those correlations were all bad. So this is the LOO can only sometimes be used. But if you read the paper about LOO, they talk about why the other information criteria are also not good. So from a model comparison point of view, it's not good at best. It's impossible. In this case, if one or more of the models that you're comparing have very bad LOO, you can't use it in the comparison.
Then follow-up question. The LRO is calculated by leave one participant out.
Yes.
But I could also define it differently, that it leaves one item out.
It could,
the
yes.
way I define the LRO is also, there's a variety, and maybe I could then start again and say, okay, let's define it differently to get an LRO that I can use actually.
Yes and no. I don't know, and I had this conversation when Jihong and I were working on the other model fit issue. We had this conversation. We tried to find a paper in psychometrics where we left one item out, because I think that would give you a good idea of person fit data. But we haven't found, or we just didn't find, it may exist, a paper or research where that had been done before. And I haven't had a chance to try it. So that would be an avenue for research to see how this works.
Okay.
If you got time on your hands.
But the default is leave one participant out.
That's right.
Okay.
That's right.
Okay.
Yes.
Is it like jackknife, so you're reducing the data set, or is it here with replacement, like bootstrapping?
It's a jackknife, where you take one out, almost like cross-validation, where you take one out, estimate a model, and predict what the values of the observed variables to be for the one left out. I think that's jackknife, if I'm not mistaken. So, yeah. So it's not working. Whatever it is, it's not working. But yes. So yeah, my initial impression of reading this was correct. When we look at the full model comparison, which is down here, pardon for the scroll. Here we go. Nope. What just happened? Oh, I know it. I had garbage there. When I looked at this at first, I said, oh, this says the model. The top model up here is the one that says it suggests. But we know we gave it values that were sort of incoherent at best. Were very bad, as it described. So you give it very bad values, it really gives you a result that doesn't make any sense. Yeah, that right there, that look. Lisa's look. We need a Lisa reacts to this. Yes, please.
But is it can I see from the negative value itself that when something wrong, is it usually bigger than 1, or?
No, so most of the time, so when you look at this output here, this is on the log density set. It's log likelihood. The values I was showing you prior to this, so the output is in this term. But if you take -2 and multiply it, you get it on the information criteria set. And so when you do the comparison, it's still using this because everything else is compared with -2. I don't know why they do that now.
And also when I have 3 models and for 2 of them I can't calculate the LOO, isn't that a poor argument for the first model?
Yeah, that's not a great...
So I have to go to other criterion to make a point.
I would look at the absolute fit, and I'd say because the second models seem to fit absolutely better than the first, they would be preferred. Now in this case, they're more complex, so we don't know if that complexity we should penalize how good that fit is based on complexity or not, but I would argue that this would be a much better fit to the data for the 2-parameter model, but that's again bias, my own bias probably.
And also a question, what could be a reason that I can't, for that problem that we can't calculate the LRO?
I'm going to give you my best impression, but I'm not confident in my result. I'm not understanding the methodology as well. But what they end up doing is use some type of Pareto distribution to simulate the process, this jackknife process of leaving one out. And in that simulation, they have found a way to have a diagnostic to say whether that simulation is effective or not. And what we're getting from this is it's really not that effective at it. I don't know why that's the case. I don't know what's happening as well. I've read the manuscript, but I haven't invested enough time to fully understand the methodology. And that's where the limit of my knowledge is. I apologize. Yes.
Do you do in regular sensitivity analysis? So, for example, split halves.
You could do that, absolutely. And in fact,
you do it in practice? Or?
No, I don't. So that's a very big disconnect between machine learning literature and psychometrics. Whereas psychometrics, we look at model fit for all of our model to all of the data at once, but we could easily do a split half, or we could do a training data set and a testing data set for cross-validation purposes. And there are people who've studied that. I'm not as familiar with that literature as well. I mean, perhaps that's what we should be doing here. Perhaps that's an easier way of going forward. But I haven't gone there because my training and my history has been led to be, okay, I'm in the psychometric field, I need to speak in this way. There is literature, I have seen it, I haven't read it thoroughly or ingested it thoroughly, that compare the two, but it would be nice to see that as well. Because that might be a way out of this mess right here. Yes.
Doesn't WAIC also use person livelihoods?
Yes, it does.
And why could it be calculated?
We could, absolutely we could.
I thought there was something wrong.
No, I couldn't calculate it because I threw away my output when I saved the chain. Now, if I go back and I saved WAIC, I definitely could. And that's where I started to, and I was like, so here, let me be more specific. To build those files so we wouldn't have to wait, I saved the LOO output. I didn't save the WAIC output, and that's why I can't switch to WAIC. There is a connection between WAIC and LOO. Like WAIC is, I want to say, if I'm remembering the literature correctly, is the asymptotic version of LOO. LOO is more so for like finite samples, whereas WAIC is where it's supposed to converge to in large samples. But I may be mistaken about that. But that would be where I would go next, is WAIC. And because I feel terrible that I'm like up here stumbling over this, when it's Lisa time, I'm going to calculate that, and I'm going to come back with WAIC this afternoon. Okay? So thank you for asking.
Can I ask a question?
Yeah, please do.
Is Bayes factor a thing in this context?
Bayes factor is a thing. In this context, I've never seen it successfully implemented because of the calculation takes a lot of, again, another integral across the parameter space. We have a lot of parameters here. And so I've always seen Bayes factor to more limited, narrow problems. The linear model problem from before, we only had in the full example, which I didn't run in class, where we put all the predictors in, there's only a small handful of parameters where Bayes factor seems to work. In my understanding, and in the world I live in, we often, particularly because we have thousands of parameters, we'd have to marginalize across their distributions to be able to get a Bayes factor. So in theory, yes. In practice, it would be very difficult, I think. Yeah.
Me again?
Yeah.
Sorry. So if we only want to test a very specific thing in our model rather than the model fit, like some parameter restrictions and whatever, and then can we use Bayes factor, or is it again computationally intensive?
I think it's the computational intensive problem, but I may be wrong about that. So, yeah, I went to the Bayes factor and I was like, okay, let me try to apply this in my own work. And I started doing that. I'm like, ooh, from what I understand of this, it's going to be computationally infeasible, but I may be wrong about that. Okay. Other thoughts or other questions? Are you sufficiently overwhelmed? Is everybody's whelmed meter at the limit now? Oh, yes.
So it seems that it's a bit tougher to do model comparison in Bayes.
Absolutely, that is correct.
It's like it's trying, and we get some information, but in the end, there remain some questions that we have to argue.
That's correct. I've also seen versions of Bayes where people will take the posterior estimates of the model parameters and try to calculate the frequentist versions of statistics as well too, which at least gives some of an answer.
Yeah.
But but no, it's largely very difficult to do. At least for large size model. This is a very large model from this. I mean, we're estimating thousands of parameters, so that's part of the issue.
But I think maybe it's not a bad idea to do the same thing in frequent tests just to get the model comparison, but then have more information implementing the Bayesian version of the model.
Correct. That would be at least some evidence as to whether the model fit better or worse. But it's not, unfortunately, not easy to be able to do. Okay. I know 12:30 is when we're supposed to stop for lunch, but I'm out of material now, thankfully. Thankfully for you and for me. You want to go to lunch early? Would that be okay? Maybe use that extra time to restore whatever brain power is left. And then when we get back, then you don't have to talk to me. I'm going to sit up here. We'll trade places with Lisa and get the WAIC
We have
running.
to go to the keynote first.
Yes, we go to the keynote after lunch and then we come here.
Keynote in the other
And the
place.
keynote is in.
Yeah, it's in the castle, and it's basically the same place we were yesterday. So you enter through the entrance that we entered yesterday, and you go up the stairs and basically to the room where we were yesterday, but you just don't go to the left. You just
Right by where we were.
Right, yeah.
I'm
You were
taking
there
off
outside.
this room,
Huh?
or should we take our stuff?
I think we can lock this.
Yeah,
Okay. Then, yeah, I think we should lock this. And oh yeah, for your posters, thanks. Maybe just put them on the table over there, and then I have access to them. Thanks.
There's vegan meatballs in the Mensa.
Yeah.
Is that a treat? Is that good?
Yeah, it's good.
Okay.
Yeah.
I don't know. Is that good or bad? Stay away or go to it. Yeah, I was gonna say that could be like LOO. Do I need to? Is it very bad or is it okay?
It's just, at least it's a vegan option, because yesterday there was like vegetable lasagna, just cheese, that was vegetarian.
Anna, like on Monday it said it was gonna be vegan.